we have to use completing the square. The reason this makes me smile a little bit is because in grade 11, when you had parabolas, if you wanted to find the vertex, you had to complete the square of a quadratic so that it was in, right? Remember that? You had to make your parabola, I don't know if you used H's or K or P's and Q's to use. P's and Q's or H's and K's? P's and Q's. So some textbooks, I don't know who decided it's either P's and Q's or H's and K's, but it doesn't matter. You had to make your parabola look like that to find the vertex. And then you were able to graph it better to find the vertex. And the vertex was super important because then you could find the maximum. Well, along comes calculus. And how easy is it to find a maximum with calculus? You just have to do the derivative and set it equal to 0. So one of the things we joked about when we first learned calculus is all that time completing the square in grade 11, was it wasted? Well, the answer is not really, because that technique still comes back when we get to some advanced antiderivatives that have 1 plus x squared and 1 minus x squared. We're going to have to use our techniques of completing the square to look at them again. So I kind of laughed because we learned derivatives and we kind of giggled like, man, did we waste time learning completing the square in grade 11? Because finding the derivative is so much faster for finding the vertex of a parabola rather than completing the square. However, the knowledge of completing the square now comes back in integrals. Because if you can get your integral to look like 1 plus x squared on the bottom, or 1 minus x squared inside of a square root, you might be able to use tan inverse and sine inverse. I guess technically we could even put one with an x out in front and have secant inverse. So what do these look like? You start off with something like 1 over x squared plus 6x plus 10. And don't write this down, but I'm going to show you what your brain would probably do first. So in the green box, don't write it down. But in your brain might do, hey, I can move this all to the top. And be like this. Okay? And your brain might want to do something with natural logs. Because, right, if I let u equal this inside, then wouldn't I have u to the minus 1? And that's a natural log. But the problem is if you make the u equal to the inside, well then your du is 2x plus 6. And that doesn't show up anywhere to substitute that part out. So you would probably want to go to substitution first and probably want to use a natural log, but it doesn't quite work. And so now we're stuck. But if we could complete the square on the bottom, and what would that look like? Well, I would have first of all, put a space there and a space there and say I have the x squared plus 6x. If that's a perfect square, it would have to be x plus 3 all squared. But if I have an x plus 3 all squared, I need that blue number 9 inside. In order to compensate for adding 9, we would have to subtract 9 on the outside. So this completing the square lets me change the bottom to 1 over x plus 3 squared plus 1. And now it's very close to this. In fact, if I do a little substitution and let u equal the x plus 3, then du is nicely just dx. And I get 1 over u squared plus 1 du. So it's quite normal for, excuse me, for our brains to think of this one as a natural log first, because it seems to fit that. But it didn't work with our substitution. We changed that to completing the square, and now we recognize that this is actually tan inverse u plus c. So we would get tan inverse of x plus 3 plus c. So this becomes another option. Can we complete the square on the bottom to make it look like either a tan inverse or a sine inverse or a secant inverse type of question? Okay? First of all, I would think substitution. I see a function inside of another function. I see the negative x squared plus 8x minus 15. My head says, I should let u equal that inside function. Unfortunately, if I let u equal the inside function, its derivative, which is negative 2x plus 8, doesn't appear anywhere. So now I think, okay, maybe it's going to be one of these. And in this case, right, I look back at tan inverse, sine inverse. Sine inverse has the square root. It had the 1 minus x squared inside. Maybe I could rearrange that inside to look like 1 minus x squared. So I start. I have negative x squared minus 8x minus 15. Factor out the negative. Leave a space here in blue and a space here in red. And if you have x squared minus 8x, in order for that to be a perfect square, you would have to add 16, because then it would be x minus 4 squared. So I could change that whole bottom part inside to negative x minus 4 squared plus 1, or if you wanted to, you could already put it in that form. So it's really looking like 1 minus something squared. Again, we could let u equal that inside function, x minus 4. The derivative is just du is going to equal dx. And the substitution works out beautifully. So you get sine inverse u plus c, which is just sine inverse x minus 4 plus c. And our first two examples worked out perfectly to match up with sine inverse and tan inverse. But one thing I hope you're noticing from the take-home quizzes is that the AP Calculus never likes it to really just work out perfectly. They want to mess with your algebra skills at the same time. So let's throw in some extra stuff. Right? Like sine inverse and tan inverse are both 1 over. What would be extra? Well, let's not have a 1 on top. Let's have a 32 on top. This is going to mean that we're going to have to do some manipulation with that 32. Again, the bottom, I would want to do a substitution, but if I make the bottom equal to u, du would be 2x minus 4 dx. It doesn't show up. So then I'm going to go to my completing the square strategy. Okay? X squared minus 4x, that would need a plus 4 in order to be perfectly x minus 2 squared. So I have to subtract 4 on the outside. Now, first of all, we have an issue that when we completed the square, our tan inverse integral, only works if it's 1 plus. We have an issue. We don't have a plus 1 at the end. We have a plus 1, and then there's a 6 right beside it. It's a kind of an issue. We have a plus 16. So again, we need to manipulate to get this plus 1. Well, I can manipulate this by dividing everything by 16 or taking out a 1/16. And that's what we're going to do. We can either take out that 1/16, or algebraically we could multiply the bottom by 1/16, which would mean I'd also have to multiply the top by 1/16. So you can choose your algebra, it doesn't matter. Sometimes I really like the idea of factoring out. Factor out that 1/16 and see what you would get. Either way, when you simplify this, you're going to get a 2 on the top now instead of a 1. Which is still somewhat problematic because the integral only had a 1 on the top. But we could take that 2, since it's just multiplying, and bring it out in front. And we could think of this 16 on the bottom and put it inside the square root, because now I would just have x minus 2 all over 4 all squared. And now this is matching up very nicely. Okay. I'm going to actually not show you these boxes yet, because I did it in a little bit of a different way. Are you okay, first of all, if u is x minus 2 over 4, that du is 1/4? Okay, because you could make this as 1/4 x minus 2 over 4. You could unadd those fractions, and then it's a simple derivative. Okay? So if I do the substitution now, I would have 2, here I'll go back to black. I have the 2 out in front, I have my integral, and I now have 1 over u squared plus 1, and then instead of dx, I have 4 du. I can move that 4 out in front, giving me 8, and then this is perfectly tan inverse u plus c, so our final answer is 8 tan inverse, and our x, our u is x minus 2 over 4 plus c. Square around your final answer. Perfect. Now, some of you might eventually be able to go without the substitution, okay? Especially because inside, where the u would be, is in the form ax plus b, which just has a simple chain rule if you were doing the derivative, where you would have to multiply by 1/4. So if you use that strategy, you could right away say tan inverse of x minus 2 over 4. And since the simple chain rule, if I did the derivative, would have to multiply by 1/4, I have to compensate, so I divide by 1/4. This, of course, gives you 8 in the end either way. I do find for students that with sine inverse and tan inverse, people like the substitution better because it just makes things cleaner. Right? Would you think of this as a simple chain rule which had to multiply by 1/4, so you needed to divide by 1/4? Maybe not, so then the substitution makes it clean. So I showed both of those ways. I think I probably agree that I like the substitution in this situation a little bit better. All right, 3 for you to try. All right, did you complete the square on the bottom and then notice that it matches up perfectly with 1 minus x something squared? So it's just sine inverse x minus 1 plus c. How did your completing the square go? And then either multiply or factor out. I actually don't mind the factoring out idea here. Right, because if you factor out, factored out a 7/4 out in front, that would give you a 4/7. Does the same thing as multiplying top and bottom by 4/7. Still a little bit messy. We can pull this 4/7 on the top. You can pull that out in front. On the bottom, you have to put this 4/7 inside the square root. So putting the 4 inside, not a square root, sorry, inside the squared function. Putting a 4 inside, that would just be 2. Putting a 7 inside, you'd have a root of 7. So now we have a 2 over root 7 plus the x plus 1/2 all squared. Now our integral looks like this. Again, I probably would suggest, and I'll do it in both different ways. One where you just figure it out directly, and one where you let u equal 2 over root 7x plus 1 over root 7. And du is 2 over root 7 dx. And dx by itself would be root 7 over 2 du. And now I have 4 over 7, integral of 1 over u squared plus 1 times by root 7 over 2 du. The root 7 over 2 can come out in front. Give me 4 root 7 over 14. and this is tan inverse u plus c.
Hey, you need to slow down. I don't understand anything.
Okay, I'll write out the final answer, then we'll go back and explain some stuff.
Why'd you start square rooting everything? You're back and forth.
The square root of 7?
Yeah.
Okay.
Like, how'd you make everything? You just started square rooting everything. You're like, oh, that's 2 now. That's.
Okay, I will explain that. Okay, let's go.
Some explanations. You sure? Just stop writing.
Okay, so first thing we want to have explained is how this 4/7 changed to 2 over square root of 7. Okay? Would you agree that in order to use tan inverse, you need something squared plus 1? We have the plus 1, we have something squared, but we had, in that orange box, something extra in front. Therefore, you can't use the tan inverse substitution because it doesn't match up perfectly. However, 4 over 7 is equal to 2 over root 7 squared. Would you agree to that? If I can make it squared, I could add it inside with the other thing that is squared. Because if you're squaring two things, each thing gets, and they're multiplied, each thing gets squared on their own. So my goal here is to take that 4/7 that's out in front and put it inside so I have only one thing squared plus 1. Does that make sense? Where that 4/7 went. Now that I have only one thing squared, I'm going to make that my u. And then from there, I have to continue to do all the things I normally do as substitution. du is 2 over root 7, but I don't have a 2 over root 7, so I get the dx by itself by multiplying both sides by root 7 over 2. Then I can do my nice substitution. And everything multiplies out and works perfect. Other questions? Where did that 4/7 go? Why did I square root it? Great question. We needed it to look like 1 over one thing squared plus 1 in order to match up with tan perfectly. All right, I'll put up the answer for the last one, so you can check. Again, it doesn't match up perfectly, so you have to factor out a 4. Factoring out a 4 would be like pulling a 2 outside, because factoring out a 4 is like having a 4 inside that square root, and the square root of 4 is 2. Again, you can use substitution, or you can use, here's the work with the square root. That should be your final answer.